yesterday we looked at this picture, and we talked about how if we relate the parts, we get, obviously those two triangles are similar. We relate the parts, we get those three ratios up top, y over a equals x over b equals z over c. And I think yesterday we looked at, I think would have been y over a, that first ratio, and z over c, which is the last one. And we recognize that that would give me the sine function, or give you the sine, I say function, ratio, okay? The sine ratio, which was the opposite side divided by hypotenuse. Just kind of giving you a refresher on that. If I look at this here, the sine ratio, and actually let me open a different one because that one's, all right. So the sine, what the sine is doing, guys, the sine ratio, it's taking this side over here, and it's the opposite side of a particular angle. So we're looking at 39, okay? That's the opposite side of 39. That's the hypotenuse. It's taking that ratio, okay, which is these two numbers, and it is dividing them, and it gives me that quotient right there. Now the argument that we've been trying to prove to you is the fact that it doesn't matter the size of the triangle, okay? Obviously, these lengths change, but if I were to take my calculator, which this is what GeoGebra is doing, okay, it's calculator, and it's taking 9.344 and 14.848, it's dividing them, and it's giving me this quotient. And does that quotient ever change? Does that 0.6293 number ever change, even though the numerators and denominators change? And the logic of that, the reason of that, is because of the similarity statement here. As long as we have the same angle, as long as the 39-degree angle, that 0.6 number is always going to be the same, no matter whether I'm dealing with either of those two triangles, or maybe I look at that smaller triangle, or that smaller triangle, or that triangle. The relationship of the opposite side divided by the hypotenuse will always be the same ratio, always the same quotient. So that's what we talked about yesterday. Now, obviously, those things change as the quotient changes once the angle changes, right? So once the angle changes, and here we see one we've been doing with 30, 60, 90 triangles, we see that n divided by 2n equates to 1 over 2, okay? And, again, changing those lengths does not change the quotient, okay? That's a very, very useful thing for us because of the idea of if I don't have this, if I don't know that hypotenuse, let's hide that. I don't know the hypotenuse, but I know that there's a 30-degree angle in it, okay, and the opposite side and the hypotenuse always relate to one another in a 1 to 2 relationship. Can't I take that 8.971 number, double it, and now get the hypotenuse? That makes sense, everybody? Okay. Or, because of the way we've got this written, if they gave me that distance and I didn't know that one, okay, it's the hypotenuse, and that's the largest figure or largest side in the triangle. If I want to find this side here across from 30, the opposite side, I would take this 17.941 and multiply it by this scale factor of 1/2, and it's going to give me that 8.971 that I need for this side, correct? So the same thing happens when I deal with a number like that, okay? I don't necessarily have, that 0.694 number is not a really nice number to memorize, like 1/2 is. But if I take 17.941 and multiply it by 0.69465, it's going to shrink that number down to 12.463, which is that opposite side of that triangle, okay? So it's ultimately these sine, cosine, tangent values that we're going to talk about are ultimately scale factors that allow you to take one side of the triangle and either amplify it or reduce it to develop the other sides of the triangle. Is that okay with everyone? Okay. So let's go back. We're going to talk about the two ratios that I have here circled. Okay, x over b equals z over c. Okay, which just rewriting that here, so there's not 3 anymore. So looking at that set of ratios, that proportion, we know that we're allowed to interchange the means, right? interchange B and Z, and that gives me this here. Now, the reason we do that, the reason we want to interchange the means, is because the similarity statements, the similarity concept that we talked about in Chapter 7, allows me to, looking at, I guess it was X to B, looking at that segment compared to that segment, and then Z to C is that segment compared to that one, right? So we're jumping from one triangle to the next. But when I interchange the means, it now allows me to compare X to Z. So there's a comparison of one part in one triangle to another part in the same triangle, in B to C. Does that make sense, everybody? Okay. Now I'm going to say that this here, this angle right now that we're going to focus on, just keep looking at that one there and that one there. Okay. They're the same. And we want to label our sides off of that angle. So this would, just like yesterday, we called that opposite, right? This one here we called hypotenuse. And I don't know if we talked about what we call this one right here. The one that is right next to theta is your adjacent. Okay. Again, A would be opposite, C would be hypotenuse, and B would be adjacent. Anything? Obviously, some people might say, well, my hypotenuse is right next to theta as well, so that might not be the best way of describing it. But your hypotenuse is going to overtake or override, take precedence over being adjacent. Does that make sense? It is an adjacent side, but we can better classify it as a hypotenuse for the things that we're going to do. I always find the opposite side first, find my hypotenuse second, and then by default, the remaining side has to be adjacent. Right? What's going on here is, if I look at X over Z in that ratio right there, it's the adjacent side divided by the hypotenuse. And that's for this red triangle. Okay? Well, B over C, that's adjacent over hypotenuse as well. Okay? Now, as long as we keep theta the same, because that's the only variable up there in those two triangles that is shared by both triangles, right? X, Y, Z, A, B, and C, those are all different. Okay? What we're seeing here, as long as theta is the same, adjacent divided by hypotenuse of X and Z is equal to adjacent divided by hypotenuse of B and C. So using those arbitrary values of X and Z, B and C, is really saying that we're comparing any two right triangles that have the same angle theta, no matter how big the side lengths are, if they have both the same angle theta in them, and the adjacent divided by hypotenuse is always going to be the exact same quotient. Okay? And the adjacent side divided by hypotenuse, we will refer to that ratio all the time. We use it all the time. So it's nice to have a name for it. Okay? And this is just a definition. Okay? We define this ratio of the adjacent side divided by hypotenuse as the cosine. Cosine, spelled that way. Okay? And we are going to write it as cosine of theta, COS, equal to, I'm going to write A over H for adjacent divided by hypotenuse. Okay? So, reading things, you're writing, reading a paper or a PowerPoint or PDF, whatever, textbook. We'll talk about cosine in paragraph form. We'll write it out as COSINE. When they're doing work, they're doing algebra, they just write COS, and then of the angle that you're interested in. Is that all right? Okay. Now, I want to hopefully make an argument with you that makes sense. So let's do this. We just said, yesterday we said sine of theta was opposite divided by hypotenuse, right? Just now we made the argument that cosine of theta is adjacent divided by hypotenuse, correct? Okay. And if I'm just using this red triangle right now, let's say, so sine of theta would have been, what, y over z, okay? And cosine of theta would have been x over z, just using that triangle, okay? Everybody okay with that? Comfortable with that? What if I do this? What if I plug in a new angle up here and I call it beta? Okay. Could you tell me what the sine of beta would be? Sine, now if I look at beta, think about this. If I look at beta, all my side lengths have to be identified off of that. Okay? So this would no longer be adjacent. X would be what for beta? It'd be opposite. Y would be adjacent, right? And z is still, I don't know why I erased that, z is still the hypotenuse. So if I look at a sine of beta, it's still opposite over hypotenuse, but for beta, for that angle, it's going to be x over z, isn't it? Does that make sense to everybody? Cosine of beta would be y over z, correct? Still the adjacent side for that angle divided by the hypotenuse, but for us it'd be, using those arbitrary values of y, z, and x, it'd be y over z. What do you recognize about that there and that there? They're the same. So work your way back through these equations. What's that tell you about that there and that there for this triangle? If these two things are equal, what's that tell you about these two things? They're equal. Cosine of theta, guys, is exactly the same thing as sine of beta for that triangle. And likewise, I'm not going to write this, but y over z and y over z, those are equal, right? So doesn't it mean that sine of theta is the same thing as cosine of beta? Okay. Let's talk about why this is a useful relationship to know. Okay. We're going to eventually know what theta is. So let's just say theta is 20 degrees. Okay. I could say that cosine of 20 degrees is now equal to sine of beta. Do you know what beta would be? What is that? That's that angle. If this one's 20 and that one's 90, that one's got to be 70. Okay. So right there, hopefully you see those two numbers. What do 20 and 90 add up to? Sorry, 20 and 70. What do 20 and 70 add up to? Add up to 90. When you have two angles add up to 90, what do you call them? Complementary. What's the first two letters of complementary? First two letters are C and O, right? Sine and cosine differ by those first two letters of C and O, don't they? So that's the link that says when I'm dealing with a figure, a triangle, and let's say Cameron's going to use cosine of 20. Somebody else would use sine of 70 and get the same exact answer. Or using the other relationship, if I say I want to look at the sine of 20, somebody else would use the cosine of 70. They should equate. And when we look at our calculator, if we look at, I'll just use Desmos here. If I type in sine of 20, I get that number right there, right? Well, cosine of its complement then, right in the right, gotta be in degrees. Sine of 20, 0.34, cosine of 70, 0.34, right? Do any angle measurement you want here. If this is 23, this would be, what, 67? Are those numbers the same? Okay. And I could put, 67 here and 23 there. As long as they're complement angle measurements, I can find out that they're equated sine of, usually the way we write this, usually the argument is that the sine of theta is equal to the cosine of 90 minus theta. or the cosine of theta is equal to the sine of 90 minus theta. Because the 90 minus theta gives me that complement angle, right? So if my theta is 20, 90 minus 20 gives me 7. Okay? If theta is 23, then 90 minus 23 gives me 67. Does that make sense, everybody? That's a relationship that you need to know. That's a relationship that is asked about frequently on end-of-course exams. Okay? We've only got 2 or 3 end-of-course exams that have been provided, but that shows up a couple times. Okay, so they like to ask that relationship and have you understand that relationship. Okay, so here's another thing that I want to talk about real quick. If we go back to, because we're missing one ratio. So I go back to this, and I want to compare these two. If I take those two, get y over a over x, or equals x over b, interchange the means again, so that's going to produce y over x and a over b, right? If I'm looking at theta, and y is opposite, x is adjacent, right? I'm looking down here, a is opposite, b is adjacent. So these both are opposite divided by adjacent. For any two right triangles that have the same theta, the opposite divided by adjacent right here is being shown that they're equivalent. We define that. Does anybody know what we define that as? We've talked about the sine. We've talked about the cosine. What's the other one? Tangent. Okay. Spelled out, it's that. Okay. But we are going to abbreviate it in our handwritten work as tan. Okay, so we'll refer to it, we'll call it tangent. T-A-N. There are so many links and comparisons, relationships that exist right now with what we're doing and what we're going to do later on in circles. So that tangent is going to come up again, and hopefully maybe when we talk about circles, and hopefully we'll be able to kind of make the argument or the comparison of why in circles we talk about tangent as well. Okay, and all these things have a relationship back to circles. Okay? Won't you wait a few minutes, because I don't want you to miss this stuff. So tangent of theta is equal to opposite divided by adjacent. All right. So let's look at another relationship. If we know, you guys told me, and I'm going to label this as, this was y, or this was x, and this was z, right? Looking at theta, we just said the sine of theta was opposite over hypotenuse, so y over z. Cosine of theta is equal to adjacent divided by hypotenuse, and tangent of theta was opposite over adjacent, right? Okay. I'm going to look at these three ratios, and I'm going to see if I can do some work with them to figure out a relationship here that's pretty useful. And what I'm going to do is I'm going to start with these two right there. Okay. I take y divided by z. That's that ratio right there, right? I'm going to divide that by that ratio, x divided by z. Okay? And this is, guys, where it becomes important, and I've been talking about this all year. Don't just rely on your calculator, because if I didn't know what that's going to equate to, I don't know my rules of algebra, my calculator is never going to be able to tell me what that is. My calculator doesn't have a computer algebra solving system on it. Okay? So I want to figure out what that is. What does that simplify to? Do you ever remember how I divide a fraction by a fraction? Like if I had 1/2 divided by 2/3, how you do that? Yeah, multiply by that reciprocal, right? So I come up here and multiply by 3/2, gives me 3/4, right? So can't I do the same thing here? Because these just represent unknown values, unknown numbers, so let's multiply by the reciprocal. And when I do that, what happens to the z's? They cancel out. It leaves me just y over x, right? Well, what was y over x the same as? It was that, right? Does that make sense to everybody? So I get y over x when I divide these. What was y over z? What was that equivalent to? Sine, right? So my numerator right here is sine. My denominator here is cosine, isn't it? When I divide sine by cosine, what do you get? Y over x, which is tangent. So there's a relationship here that we need to know that says tangent of theta is equal to your sine of theta divided by cosine of theta. Can we look at that and deal with that over here? Let's say that we have, I'll just say tangent of, let's just give me, if I put in the number 27, gives me that decimal back, 0.509, right? Well, what we just said, then I should be able to take sine of 27 and divide that by cosine of 27. Does it give me back the exact same decimal? Okay, so that's a link, that's a relationship that is important for trigonometry. Tangent is the same thing as sine divided by cosine. Okay. Now you have to use the same theta. Okay, it has to be common. I think a lot of you guys are probably saying, well, let's get to the problems. Let's get to the actual work here, because I think as a 5th grader, 6th grader, 7th grader, it's kind of beating your head that we don't pay attention too much of why we do something. We just pay attention to how we do something. Okay, I think understanding why we can do it and these relationships that exist are going to allow you to be a lot better at learning how to do it. Okay, you have kind of met the threshold in mathematics of no longer just working with computations and calculations. Okay, that is a small aspect of mathematics. Okay, a larger aspect of mathematics is being able to understand. Okay, and to be able to explain and that kind of stuff. So that's what we're trying to get at here. You guys maybe are familiar with this phrase here. We'll say sine of theta is equal to opposite over hypotenuse. Cosine of theta is equal to adjacent divided by hypotenuse. And tangent of theta is equal to opposite over adjacent. If I take that first letter and then take that quotient, I get that synonym, or not synonym, acronym. Okay? If I take that first letter in that ratio, I get that acronym. And if I take that first letter in that one, I get that. Okay? And you guys have probably heard the phrase SOHCAHTOA before, right? Okay? The first letters of SOHCAHTOA, the S, the C, and the T, tell you what trig ratio, what the definition was, sine, cosine, or tangent. And then the last 2 letters in the correct order, numerator divided by denominator, OH, AH, OA, give you the ratio that we define sine, cosine, and tangent by. That's something new? Tell you guys remember that? Heard that before? Okay. Now you know where that information comes from, what it means, why we're getting these ratios, where the ratios come from, that kind of stuff. So let's do some problems. In this one, it says solve the triangle. Whenever you see that phrase, solve the triangle, it means find all 6 parts. Right now we only know really 3 parts. We know the right triangle, so we got the right angle, we got 54. We should know the other angle is 36, right? We know the hypotenuse is 17. We should be able to find W. We should be able to find the other leg that we don't have any markings up there for right now. And that will solve the triangle, okay? So a lot of times what this trigonometry is going to allow us to do is have a limited amount of values in a triangle, be able to use SOHCAHTOA to find all 6 parts of the triangle. Okay? So, in order to do this, one, you have to have a right triangle. Once you have the right triangle, you need 2 other parts. Okay? You need the part that they're asking for, in this case W, and then you need a known value. You need a side length. In this case, we got 17. So if I want to find W, let's just kind of work with that first. Finding W, I'm first going to look at the angle that I'm interested in. And I would assume that because it was given, most of us are probably going to look at the 54-degree angle. Okay? And then I start labeling the sides off of that 54-degree angle. So what would W be for that 54 degrees? That's the opposite side. Okay? This would be the adjacent then, right? And 17 has to be the hypotenuse. Okay? Now, if you're solving for W, you have to use the angle that you just labeled all the sides off of or in respect to. You're solving for W, so W has to be in your equation. What is the only other thing up there that you can put in your equation? 17. Okay? So you need an angle and you need 2 sides. Okay? One of those sides is going to be what you're solving for, and the other side is going to be the one that you know. So if those are the parts I'm going to use, opposite and hypotenuse, what trig ratio uses opposite and hypotenuse? Sine. Okay? So I'm going to say sine of that angle, 54, is equal to opposite, which we knew to be W, divided by the hypotenuse, which is 17, right? Okay. Now what I want you guys to know is kind of the logic that we go through here to solve this. If I was dealing with, sine of 54, because we know sine of 54, see here, sine 54. Sine of 50, I'm looking for a calculator back here real quick. My phone's not working. All right, so this is a symbol for the number 0.80901 on forever, okay? Many more decimal places. We have that now currently equal to W over 17. Does that kind of make sense? If that's the case, how would you solve for W? You would multiply by 17 here, and those are going to cancel out, right? Then you would come to this side, and whatever that number is, you would multiply by 17, correct? Okay. Well, I never really want to write it this way. I'm just kind of showing you the logic of why we do this or what we're going to do. You're always going to multiply by that denominator. They're going to cancel. And you come over here and you multiply that side by that same thing. So now you're left with 17 sine of 54, and that's your W value. That's the exact value of W. Okay? Now, if I gave you that number, told you go put this on the number line, not many people are going to be able to do that, right? So it would probably be better if we could change that to a decimal. So this is where we grab our calculator and we type in 17 sine of 54, okay? And make sure we're in the right mode. I am in degrees, I believe. Yeah, I am in degrees. So that is then the length of W. Is that okay with everyone? Okay. What I would caution you against doing, okay, is, if I take 17 and I multiplied it by sine of 54, but sine of 54 was a decimal, as that, do you see how the number is no longer actually 17 sine of 54? Okay? It's been cut off, right? It's been shortened. Okay? It's been rounded, and that's an issue. Okay? So we would rather leave it at sine 54 than at 0.809. Does that make sense? So it's always kind of a learning curve for people to do their algebra by hand when the work has words in it, like sine, cosine, tangent. Eventually you guys will deal with logarithms, stuff like that. But you treat the sine 54 is just the exact same thing as what like radical 2 would have been. They're symbols for other numbers, right? So if they're a symbol for a number, that means they are a number, so you treat them like numbers. Okay? So that's W. Can we find Z up here? Okay. Now here's the thing. There's a lot of different approaches here, guys, and I'm not going to cover every one with you, but we know that number right there is 13.753, and I've rounded it. I probably don't want to use that number in that format to help find Z, because what am I going to have to do with that number? I'm probably going to have to round it, right? And if I use that number rounded to find Z, did I really find Z, or did I find something close to Z? Found something close to Z, right? So when you guys are doing these questions, when you find one value, it opens the door to multiple opportunities, multiple chances, or I guess techniques to find other values. Try to use the approaches that eliminate using rounded values. Okay, and that's going to make your life a lot easier later on if we understand that concept. So I'm going to use to find Z. I'm going to use the 54 again and the 17 because neither of those were rounded. Correct? This would be the adjacent side. This would be the hypotenuse, correct? Okay, so the adjacent side and hypotenuse, what trig ratio do you use there? Cosine. So say cosine of 54 is equal to Z over 17, right? Multiply both sides by 17. And there's my Z value. So see what that is, 17 cosine 54, and there's my Z. Okay. And I just want to show you that rounding kind of issue. How'd that triangle look? Okay. So if I was dealing with this to be 54, this would have been Z. We found this to be 13.753. I should leave it that way. And I wanted to find Z using that. This would be opposite, right? This would be adjacent, right? Could I say that tangent of 54 is equal to opposite divided by adjacent? Does that make sense, everybody? Okay. Now, this is, and you're going to see a lot of these, so you have to learn this process. That's just a number, right? Or represents a number. So just like before, when I multiplied both sides by 17, because that was a number, I'm going to multiply both sides by Z because it represents just a number, right? So multiply by Z, and they're going to cancel. Come over here and multiply by Z. So get Z tangent 54. Z tangent 54 is equal to 13.753. Now, tangent of 54 is just a number, isn't it? Tangent 54 is that number right there. So really, I got 1.37638192047 equals that number, right? Well, what would I divide both sides by to get 1Z? You would divide both sides by that number, wouldn't you? By the coefficient. This is just a coefficient for Z. And this is what I was talking about. There's a learning curve for people to understand that that's just a number. So it's a coefficient for that variable. So to isolate that variable, I divide by it, come over here, divide by tangent 54, and I get z equal 13.753 divided by tangent of 54. Now, if I do this right, it should give me the same 9.99 number, right? Or something close to that. We've already found z a different way, a more accurate way, you're going to find out. But if I take 13.753 divided by tangent of 54, hit enter, it gives me that number right there, correct? Okay, which probably for all practical purposes, for our applications, probably isn't a bad thing, okay? But you start to see, if I would have rounded this to like 5, now you start to see that there's quite a bit of rounding error in those two answers now, right? And even if I would have rounded that to 8, because a lot of people want to do that, you now see that there's a drastic amount of rounding error, okay? So if I can avoid that rounding error, I'm going to do that. Does that make sense? Okay. How can I eliminate all rounding error? Well, what is that number? 13.8, really? As an exact value, wasn't it 17 cosine of 54? Okay. No, sorry, it wasn't that. What was it? Was it the sine? It was 17 sine of 54. Okay. So I can put the exact value in there, and now there's absolutely no discrepancy between those two things, right? Okay. How can I check to see if I've done all this right? Because now we've got this value, we've got this value, and we've got the hypotenuse. What geometry will tell me that all these values are correct? If it's a right triangle, I know all three parts. Pythagorean theorem, right? Now, with Desmos, you can double click on these things, and I think you might even, yeah, if you click the equal sign, it will highlight. You hit Control C, and that will cut that value. I come down here and hit Control V, and it will paste it. I'll raise it to the second power. I'm then going to add to it. And now I need this number. So I'll Control C that, come down here, Control V. I will square it. I don't think I squared it right. Did I add a 6? Okay. Shift. There we go. 2. And it gives me that number right there. Does that tell me I've done everything right? Because what is 17 squared? My hypotenuse squared is 289, right? Well, what about that 0.0001 there, right? Why does that happen? I took these two numbers, right? Now, the way your computers work, the way your any calculator you have is going to work, we're not confident in what that number right there should be, okay? Because we don't know the number that came after it, the way it's being displayed to us. Does that make sense? So that number that comes after that might actually be a 3, okay? So that would have told me to keep that 4 to 4. Does that make sense? But that number right there could have been a 3, and the number that comes after it is 5 or bigger. That number after it would have told the computer to round that 3 to a 4 like it did. Does that make sense? And the same thing happens down there with the 7 on the 9.99 number. So because of that, we get a little bit of rounding error. Okay? It's very, very small, right? So it's not a big deal. We can make the argument that they're the same. But that's the reason for that. If I want to eliminate rounding error, okay, we could do this. Was it 17 cosine of 54 one side length? And that's the exact value, right? So square that. Add to it 17 sine of 54. That was the other side length, right? Square that. Absolutely no rounding error because I never used a rounded value, right? There's no compounded rounding error. It's all exact values. So that's where I get the 289 exactly. Here's another question. Okay, and this will be the last thing before you go to lunch. I found this side to be 17 cosine 54. What if I did 17 sine of 36? Why does that work? Okay, so this 54 and this 36 are complementary angles, right? So 36 would be here, correct? And if I wanted to find out what the z is, I could say sine of 36 is equal to z over 17, opposite of our hypotenuse, because now this side, z would be opposite, and multiply both sides by 17, and I get the same exact value. All right? That's going back to the idea that sine and cosine are complements. I could also do the same thing for that 13 number. I could say 17 cosine of 36 would be that number. All right? I know we only did one example. By far, not enough to really get a hang of this. I wanted to show you the different ways that you and your neighbor might do a problem. Does that make sense? And use all the different relationships that you and your neighbor could use differently, but still arrive at the same answer. All right. Next week, Monday, we'll probably spend a little bit more time doing some more examples. I do have an assignment open. I want to see what you're able to do. Right now, view it as being due on Monday, but we'll talk about that and see if we need to change that due date and that kind of stuff when Monday gets here. Other than that, you guys have a great weekend. Man, I'm letting you out early. Thank you.